Welcome back to Research Unraveled, the podcast where we break down the latest research papers into simple, digestible insights. Today, I'm joined by Maya, a leading AI researcher, to discuss a fascinating paper about automating CUDA kernel engineering. Maya, welcome to the show.
Thanks for having me, Alex. I'm excited to dive into this. It's a really interesting area with huge potential impact.
So, CUDA kernel engineering. That sounds pretty technical. Can you give us a high-level overview for those of us who aren't deep in the weeds of GPU programming?
Absolutely. Think of it this way. Modern AI, especially deep learning, relies heavily on GPU's graphics processing units. These GPUs are incredibly powerful for parallel computations, which are essential for training and running large AI models. CUDA is NVIDIA platform that allows us to program these GPUs directly. A CUDA kernel is essentially a small program that runs on the GPU. Optimizing these kernels is crucial for making AI models run faster and more efficiently, but it's a very specialized skill.
So, this paper is about automating that optimization process.
Exactly, the paper titled The AI CUDA Engineer, Agentic CUDA Kernel Discovery, Optimization, and Composition introduces a framework that uses large language models, LLMs, to automatically translate PyTorch code, a popular AI framework, into CUDA kernels and then iteratively improve their performance. They call their system the AI CUDA Engineer.
That's ambitious. What are the key components of this AI CUDA engineer?
The system works in four main stages. First, it converts PyTorch code into a functional representation. This means taking object-oriented code, like an N module in PyTorch, and turning it into a function that explicitly takes all the parameters as inputs. This makes it easier for the LLM to understand the core computation. Second, it translates this functional PyTorch code into a CUDA kernel. This is where the LLM writes the actual code that will run on the GPU. Third, and this is really cool, it uses an evolutionary optimization process to improve the kernel's runtime. It generates multiple versions of the kernel, tests them, profiles them to see where the bottlenecks are, and then uses the LLM to edit and improve them. It's like an AI engineer constantly refining the code. Finally, the system builds an innovation archive of discovered kernels. This archive is then used to provide examples to the LLM when it's working on new tasks, a technique called retrieval augmented generation, or RAG.
Okay, so it's learning from its past successes. That makes sense. What kind of results did they achieve?
The results are impressive. They tested their system on 250 PyTorch operations from a benchmark called Kernel Bench. They found that the AI CUDA engineer could successfully translate over 91% of the PyTorch code into working CUDA kernels. More importantly, it optimized 75% of those kernels to perform better than the native PyTorch implementations. And in some cases, they saw runtime improvements of 50x or more, especially for complex operations like fused 3D convolutions.
Wow, 50x, that's a huge speedup. What does fused mean in this context?
Fusing operations means combining multiple operations into a single CUDA kernel. For example, instead of running a convolution, then a re-LU activation, then a normalization, you can write a single kernel that does all three at once. This reduces memory transfers and kernel launch overhead, leading to significant performance gains. It's a common optimization technique, but it requires careful coding.
So the AI is figuring out how to fuse these operations effectively.
Exactly, and it's not just about speed. The system also ensures that the kernels are numerically correct. It compares the output of the CUDA kernel to the output of the original PyTorch code to make sure they're doing the same thing.
You mentioned an evolutionary optimization process. Can you elaborate on that?
Sure, the AI CUDA engineer uses the LLM to generate multiple candidate kernels. It then evaluates each kernel for correctness and runtime performance. The best performing kernels are then used as parents to generate new kernels. The LLM can introduce variations, like changing block sizes, using different memory access patterns, or even fusing operations. It's like a natural selection process, where the fittest kernels survive and reproduce.
That's a clever approach. What about the Innovation Archive in RAG? How does that work?
The Innovation Archive is a collection of all the CUDA kernels that the system has successfully translated and optimized. When the AI CUDA engineer is faced with a new task, it uses RAG to retrieve similar kernels from the archive. It does this by computing text embeddings of the PyTorch code and finding the k-nearest neighbors in embedding space. The corresponding CUDA kernels are then provided as examples to the LLM, giving it a head start on the translation and optimization process.
So it's learning from its past experience and applying that knowledge to new problems.
Precisely. And they found that RAG significantly improved both the translation and optimization capabilities of the system. In some cases, it enabled the successful translation of operations that had previously failed.
This sounds like a significant step forward in automating GPU programming. What are some of the limitations of this approach?
There are a few. First, the current system focuses primarily on inference time computations and the forward pass. It doesn't handle the backward pass or gradient calculations, which are essential for training AI models. Second, the system can sometimes be tricked by non-robust correctness tests. The authors mentioned that they had to make the evaluation harness more robust after discovering that the AI had found a memory exploit. This highlights the importance of careful human verification of LLM-generated code. Finally, the system can struggle with more advanced hardware-specific optimizations, like using Tensor Core WMMA capabilities. These require a deeper understanding of the underlying hardware architecture.
That makes sense, so what are the broader implications of this research? What are the potential ethical considerations?
The broader implications are huge. Automating CUDA kernel engineering could make AI development much more accessible and efficient. It could allow researchers and engineers to focus on higher level tasks, like designing new models and algorithms, rather than spending countless hours hand tuning low level code. However, it also raises ethical considerations. Automating specialized engineering work could have economic and workforce implications. It's important to consider how these tools might impact the job market for CUDA optimization engineers. Also, as with any AI system, it's crucial to ensure that the generated code is safe, reliable, and doesn't perpetuate biases.
Definitely important points to consider. What are some potential future directions for this research?
There are many exciting possibilities. One direction is to extend the system to handle the backward pass and gradient calculations. Another is to improve its ability to leverage hardware specific optimizations. It would also be interesting to explore how compilers can be used to aid the LLM in translating and optimizing code. And of course, training open source models with the verified kernel library that they are releasing is a very exciting direction.
This has been incredibly insightful, Maya. Thanks for breaking down this complex research for us. It sounds like the AI CUDA Engineer is a promising step towards democratizing access to efficient AI computing.
My pleasure, Alex. It's definitely an exciting area to watch.